Have you ever noticed how train tracks, highways, or even rows of lockers seem perfectly aligned? That's geometry at work, and today, we're diving into the world of parallel lines and transversals. By the end of this lesson, you'll know how to spot relationships between angles, use postulates to prove lines are parallel, and solve problems that show up everywhere, from road designs to architectural blueprints. Here are some definitions. Parallel lines, lines in the same plane that never intersect. Transversal, a line that crosses two or more other lines. Angle relationships. When a transversal crosses parallel lines, it creates corresponding angles, alternate interior angles, and same-side interior angles, each with specific properties. Postulates and theorems. Rules like the corresponding angles postulate and the alternate interior angles theorem help prove whether lines are parallel. Urban planners use parallel and perpendicular lines to design road grids. Carpenters ensure walls are perfectly aligned using these concepts. Graphic designers apply these principles to create perspective drawings that look realistic. Let's say we have two parallel lines cut by a transversal. One of the corresponding angles is 70 degrees. What's the measure of its matching corresponding angle on the other intersection? Solution. By the corresponding angles postulate, corresponding angles are equal when lines are parallel. So, the other angle is equal to 70 degrees. Boom! Easiest win in geometry. Now, let's make it trickier. A transversal cuts two lines. One alternate interior angle measures 65 degrees, and its partner alternate interior angle is labeled 3 times x minus 5 degree. Are the lines parallel? If so, find x. Solution. Alternate interior angles are equal if the lines are parallel. 65 is equal to 3 times x minus 5. Add 5 to both sides. 70 is equal to 3 times x. Divide by 3. X is equal to 70 divided by 3 is almost equal to 23.33. Yes, the lines are parallel because the angles are congruent when x is almost equal to 23.33. Imagine you're designing a bike lane that runs parallel to a major road. A surveyor measures the intersection angles formed by a cross street and finds one angle to be 112 degrees. The city's safety guidelines require all same-side interior angles to sum to 180 degrees for the streets to be considered parallel. Is your bike lane safe? Solution. Same-side interior angles sum up to 180 degrees if the lines are parallel. 112 degrees plus other angle are equal to 180 degrees. Other angle is equal to 68 degrees. If the surveyor's measurement matches 68 degrees, your design is safe. If not, time to remeasure before someone ends up in the wrong lane. Today, we learned how parallel lines and transversals create predictable angle relationships, how to use postulates and theorems to prove lines are parallel, and how this knowledge helps in real-world design. Key takeaways. Corresponding and alternate interior angles help us prove lines are parallel. Same-side interior angles are supplementary when lines are parallel. These principles are everywhere: roads, railways, architecture, and art. Next up, we'll apply these skills to parallelograms and their properties. Trust me, you're going to start seeing geometry in every single building you pass.